Okay, so we're going to do 2D airfoil analysis in like 10 minutes. So. Okay, so there's something called flat plate theory. And flat plate theory says if I take an infinitely flat plate and throw wind at it, I'm going to have some drag and some lift, okay? If I rotate this flat plate at some angle, so say I'll take this as the CG and I rotate it about this angle, I'm still going to say that this is lift and this is drag. But what I'm going to do is I'm going to figure out what's called the Aerodynamic Center. I'll get to that in a sec. And I'm going to draw lift here and drag here. And I'm going to call this angle between the rotated airfoil and the free stream airflow as alpha, which is called the angle of attack. Now what this means, when I write it like this, it means lift is always up, no matter what, even if the thing is rotated. And so if I have a wing that's straight up like this, and this is my aerodynamic center, I still have lift and drag this way. But what it means is that if my angle of attack is 0, I have no lift and a lot of drag. If I have angle of attack is 90, I have the same thing, no lift, a lot of drag. If I'm in between there, I'm going to have a little bit of lift and a little bit of drag. And the point is how do I compute that? Okay? So people have gone through and they've said, well, for a flat plate, I'm going to use some circulation integrals and Kutta-Joukowski theorems and triple like volume integrals and stuff like that. And what they found out was that the lift coefficient is equal to some polynomial. It's linear, and it has a what's called a 0 angle of attack lift coefficient plus CL alpha times alpha. And it varies linearly. So if I plot this on a graph, I'm going to have angle of attack, and I'm going to have my alpha, I'm going to have CL0 here, and then my slope is going to be CL alpha. Okay? They did the exact same thing for drag. They said, okay, I'm going to write it as a polynomial, and I'm going to write CD0 plus CD alpha, alpha squared. So again, if I plot that on a figure, I've got alpha, I'm going to have CD0, and I'm going to have some bucket like this. And this is going to be my drag coefficient. Okay? So the rule of thumb, obviously, is if I fly at an angle of attack of 0, I'm going to get no lift. Or I'm only going to get this much lift, depending on my airfoil. If I increase angle of attack, I'm going to get more of a lift coefficient, which is going to feed into my overall lift, depending on my velocity, and I'm going to get lift there. So if you notice, this aircraft, when it's taking off, is at an angle of attack that's non-zero, because I want to be able to take off. Once it's cruising, if you notice this, the aircraft shape, if you look at it on the side, what do you notice about the bottom of this wing here? It's flat. What do you notice about the top? It's a little curved. So this is actually what's called a cambered airfoil. And so what the shape and camber and thickness of the aircraft, of the wing, affects these two parameters here. And so these guys back in the day came up with what's called the Nakka Nomenclature. I guess I could call it a nomenclature. And I'm going to Google this because I always forget what the numbers mean. Nakka Nomenclature. Let's see. Here you go. Nope, that's not what I want. Yeah, this is it. Okay, so for example, let's say I have a Nakka 2412 airfoil. So the airfoil shape is called 2412, just like a name. You know, like your name is Philip. I'm going to call this guy 2412. It means that the maximum camber. So what is camber? Okay, so here's an airfoil. Let me draw an airfoil with some camber here. That's a terrible wing, but okay. This is camber here. So the airfoil is curved, right? So you can imagine a symmetric airfoil is flat, this one has some camber to it. And then if I write this as x, and this is x equals 0 here, and this is x equals c, so c is the chord length, so that's all the way down there, it's saying that the maximum camber, the location of the maximum camber, is 2% from the leading edge. And so the leading edge is obviously here. So for Nakka 2412, if I go 2% of the chord, that's where the maximum camber is. And then, wait, no, the maximum camber of 2% is located 40% from the leading edge. Man, I had that completely backwards. Okay, so this is why I Googled this. Okay, so the maximum camber, max camber, is 2%. So it's not very much camber, and it's 40% from the leading edge. Okay? All right, so let's say that one more time. So 40% from the leading edge, the maximum camber is 2% of the chord. Okay? And what do the last two numbers mean? 12, the last two numbers, 12, are the maximum thickness. And so in this case, it's 12%. Okay? So if I have a Nakka 0012, how much camber do I have? 0. And so this is a symmetric airfoil. How thick is the airfoil? 12% of the chord. So it means it's going to be symmetric, top and the bottom are the same, and it's got a 12% thickness.
You said 20%. You said 12% of the chord?
12% of the chord, yeah. So if I take...
What specifically is that? Like, what do you mean by the chord?
Oh, the chord is this length. This is the chord length. So say the chord length is 5 inches. The maximum thickness would be 12% of 5, which would be, what, 6.6 inches? The other thing that's really neat about symmetric airfoils is that for symmetric airfoils, CL0 is 0. So if I have a symmetric airfoil and I'm flying and my angle of attack is 0, I will generate no lift. So some people like that because if I want to fly upside down, now I've got a symmetric airfoil. But for say an aircraft like this, what if I always want the aircraft to fly flat? You know, at an angle of attack of 0. Well, then I need an airfoil that's going to generate some lift even when the aircraft is flat. So I camber the airfoil a little bit, and so that way when my angle of attack is 0, as long as I'm flying fast enough, I'll still generate some lift. Okay? These drag polars, CD0, CD alpha, CL0, CL alpha, CD0, and CD alpha, all depend on the shape of your airfoil. So if you change your Nakka number, you change your aerodynamic characteristics. So what matters? Well, there's a couple things that matter. One is your lift to drag ratio. What do you want this to be? Really big or really small? Really big. You want to maximize lift and decrease drag. Now here's the problem. This is a function of angle of attack. Okay, so now things start to get complicated, right? So it means that I need to first figure out how fast my aircraft is going to fly. Once I determine how fast it's going to fly, then I can compute, say, drag from that. But then I need to back out, okay, do I have enough lift from that? So then I need to compute my angle of attack, make sure I compute enough lift from that. And then once you back out your angle of attack, then you can compute your thrust because you know what drag is, and you can size your motor, make sure it's 0.5. And then you just iterate and turn the crank over and over and over again until you converge on something that works. You see how all those tie together? That's what the PVF guys did last year too. It's a lot. It's like you have to kind of make an entry point. Just make a guess. I'm going to make my cruise speed 20 meters per second. Okay? And I'm going to make the area of my wing is this, and my airfoil is this. If I fly at that speed and the weight of my aircraft is this, how much lift do I need? Well, you can compute that because lift needs to equal weight. Once you have lift, you can back out angle of attack. Once you have angle of attack, you can compute drag, and then you can compute thrust. And then you iterate again. And then you start over, exactly. All right, let's hit the button again. I'm going to pull up the computer, and I'm going to show you really quickly just like a quick airfoil design here. Oh, now I gotta stand up on this again. Maybe the on button will work.
There you go.